Okay, we are going to be looking at metric measurement. We have been discussing matter, and we realize that matter is anything that has mass and occupies space. And we talk about matter, we discuss physical and chemical properties of that matter, and many times we have to use quantitative observations or data to do that, which means we have to use numbers. Quantitative data, quantity being numbers. So we need to make sure we understand the metric measurement system. Today, you're going to be filling in some notes that look like this, that go right along with these slides. Plus, you'll be answering some questions that you'll have to sometimes pause the video and go back to the notes to fill in what's missing. And you're going to be filling in what's in red. So, measurements. The quantitative observations that we make always need to include numbers and some units. So we don't just say 5 or 7, we need to say 5 milliliters or 5 kilometers or 5 grams, whatever that particular substance is that we're discussing. So there's two systems that are commonly used. There's the English system, which we use here in the United States, and a couple other countries use it, and then the metric system, the common system we use in sciences, and most people use this system throughout the world. So we in the United States kind of use a little bit of both, but in science, we are always going to be using this metric system. So in the English system, for example, if I say how tall I am, I'm 5 feet 10 inches tall. We discuss things in miles, or we do temperature in Fahrenheit, like it's 72 degrees Fahrenheit in this room right now. We also have the foot, the yard, the pound. These are all English units of system. Now, the one thing that's unusual about the English system is you have to memorize certain things, like there's 5,280 feet in a mile, or there's 3 feet in a yard, or there's 12 inches in 1 foot. In the metric system, it is not done that way. It is a system in which you are just using decimals the whole time. And so let's watch a quick little video. After the video, I'm going to teach you some key ways of measuring length, mass, and volume in chemistry. So let's watch this quick video.
What does the French Revolution have to do with the time NASA accidentally crashed a $200 million orbiter into the surface of Mars? Actually, everything. That crash happened due to an error in converting between two measurement systems, US customary units and their SI or metric equivalents. So what's the connection to the French Revolution? Let's explain. For the majority of recorded human history, units like the weight of a grain or the length of a hand weren't exact and varied from place to place. And different regions didn't just use varying measurements, they had completely different number systems as well. By the late Middle Ages, the Hindu-Arabic decimal system mostly replaced Roman numerals and fractions in Europe. But efforts by scholars like John Wilkins to promote standard decimal-based measures were less successful. With 250,000 different units in France alone, any widespread change would require massive disruption. And in 1789, that disruption came. The leaders of the French Revolution didn't just overthrow the monarchy. They sought to completely transform society according to the rational principles of the Enlightenment. When the new government took power, the Academy of Sciences convened to reform the system of measurements. Old standards based on arbitrary authority or local traditions were replaced with mathematical and natural relationships. For example, the meter, from the Greek word for measure, was defined as 1/10,000,000th between the equator and North Pole. And the new metric system was, in the words of the Marquis de Condorcet, for all people, for all time. Standardizing measurements had political advantages for the revolutionaries as well. Nobles could no longer manipulate local units to extract more rent from commoners, while the government could collect taxes more efficiently. And switching to a new republican calendar with 10-day weeks reduced church power by eliminating Sundays. Adoption of this new system wasn't easy. In fact, it was a bit of a mess. At first, people used new units alongside old ones, and the republican calendar was eventually abandoned. When Napoleon Bonaparte took power, he allowed small businesses to use traditional measurements, redefined in metric terms. But the metric system remained standard for formal use, and it spread across the continent along with France's borders. While Napoleon's empire lasted 8 years, its legacy endured far longer. Some European countries reverted to old measurements upon independence. Others realized the value of standardization in an age of international trade. After Portugal and the Netherlands switched to metric voluntarily, other nations followed, with colonial empires spreading the system around the world. As France's main rival, Britain had resisted revolutionary ideas and retained its traditional units. But over the next 2 centuries, the British Empire slowly transitioned, first approving the metric system as an optional alternative before gradually making it official. However, this switch came too late for 13 former colonies that had already gained independence. The United States of America stuck with the English units of its colonial past, and today remains one of only 3 countries which haven't fully embraced the metric system. Despite constant initiatives for metrication, many Americans consider units like feet and pounds more intuitive. And ironically, some regard the once revolutionary metric system as a symbol of global conformity. Nevertheless, the metric system is almost universally used in science and medicine, and it continues to evolve according to its original principles. For a long time, standard units were actually defined by carefully maintained physical prototypes. But thanks to improving technology and precision, these objects with limited access and unreliable longevity are now being replaced with standards based on universal constants, like the speed of light. Consistent measurements are such an integral part of our daily lives that it's hard to appreciate what a major accomplishment for humanity they've been. And just as it arose from a political revolution, the metric system remains crucial for the scientific revolutions to come.
So, by standardizing measurement, we are able to buy, sell, and trade goods. But in science, we're able to speak the same mathematical language. And so we use the metric system in science. And so the metric system was developed, as we heard, in the 1790s by the French. And it's called the International System. It's abbreviated SI because the French would call it Système International, which stands for SI. Is the abbreviation for it. It's a decimal system based on powers of 10. So unlike the English system where you have to memorize 12 inches a foot, for example, in the metric system, we can talk about smaller or larger things by using prefixes and just doing things in powers of 10. And I'm going to teach you that in a second. There's a few key units we're going to be using. Again, you're filling in the notes that go right along with you, so you can always pause the video and add those to your notes. We're looking at the length, which is the meter, the volume, which is the liter, mass, which is gram, and temperature today in Kelvin. We're also going to look at these other 3 down the road, which are energy, time, and amount of substance, which are joules, seconds, and mole, respectively. So the first one we're going to look at is the unit for length. The definition is just the extent of an object from end to end. The piece of equipment that we're going to use to measure length in the chemistry lab is the meter. The units they use, we're going to use meter, and the equipment we're going to use is a meter stick or metric ruler. Now, when we measure things, we have to measure things precisely, and the precision of the measurement depends on the piece of device we're using. So there's a rule we need to understand, and it's called a significant figure rule, and it's rule number 1, which states that to measure the number of digits you are certain of plus 1 more. Measure what you are certain of plus 1 more digit. What does that mean? Well, let me show you a couple examples. First of all, if I have a little meter stick over here or metric ruler, and I'm going to measure the length of this red line that we see here. Let me enlarge that. I see that we go in increments of 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 centimeter. So these are in centimeters here. And so I see that I'm at 1 centimeter here, and it looks like I'm between 1.0 centimeters and 1.1 centimeters. So I'm certain that this red line is somewhere right between there, and it looked like it's not right at it, so it didn't draw a line perfect there. So I think it's going to be right between those. So I'm going to measure what I'm certain of plus 1 more digit. So that's 1.05 centimeters. What I'm certain of this because that's how precise my piece of equipment is, plus 1 more measurement. All right, let's go ahead and measure this green line here. So I see this green line down here. It looks like it's exactly to me, no, here's 2.5, here's 2.6, 2.7. It looks to me like it's between 2.6 and 2.7. I'm certain that it's between there. So according to the rule, I measure what I'm certain of plus 1 more. All right, I'm certain it's between 2.6 and 2.7. It looks like it's directly between both those. So I'm going to go ahead and write 2.65 centimeters. We can also change this to millimeters. A millimeter is a tenth of a centimeter, and so there's 10 millimeters in a centimeter. So to move that decimal over, it would be 26.5, and I'm going to teach you how to do that at the end of this lesson. So let's go ahead and look at a couple rulers here. Look at this ruler on the top and the one on the bottom. We see the one on the top is much more precise because it has more graduations, more markings. In fact, they go in increments of 0.1. And these ones down here go in increments of just 1, 2 to 3. So I go 1, 2, 3. So when I measure this one, I measure what I'm certain of plus one more digit. Down here, I measure what I'm certain of. I'm certain that it's between 2 and 3 plus one more digit. Notice the difference between those two. This is significant figure rule number 1, in which we measure what you're certain of plus that one estimate, what you're certain of, plus one more digit. So let me do an example, one more example, and then I'm going to have you do a couple. Let me measure the body of this beetle. And I can see the body of this beetle. It looks like to me this goes in increments of 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. It looks to me like it's right between 1.5 and 1.6. So I would say that this is 1.55 centimeters is the length of this beetle. What I'm certain of, plus one more digit. So let's have you go ahead and do one here. Please measure the length or the diameter of this penny. Please do that now. Thank you. If you would also measure the diameter of this steel bar. Notice the ruler on the left is not as precise as the one on the right, so your measurement would be slightly different. So please tell me the measurement for that on the left. Please also tell me the measurement for that on the right. Excellent. Now we're also going to, besides measuring length, we have to measure volumes of liquids, for example, or sometimes volumes of solids, the amount of space they occupy. So the volume is the amount of space occupied by an object. If it is a liquid, if we use liquids, we use the unit liters. And the piece of equipment we use in the lab is a graduated cylinder. It just so happens that most of the time we measure in milliliters, which is a thousandth of a liter when we're measuring in the lab. And the reason we use a graduated cylinder is because it has many graduations, more markings, it's more precise. So remember, there's two key rules which we've gone over before when you read a graduated cylinder. You want to read at eye level, and you read the bottom of the meniscus. Remember, the meniscus is that little curved line. And so if we see this little curved line that goes here, you read the bottom of that line is when you're reading it. So let me go ahead and measure this particular liquid. And notice it goes 40, 41, 40, 41, 42, 43. It looks to me it's right at 43, okay? Since I think it's right at 43, when I measure this, I'm going to say it's 43 milliliters, but that's not correct. It's 43.0. I'm measuring what I'm certain of plus one more digit. So I'm being that precise because that's how precise my piece of equipment is. Let me do 3 more examples for you, then I'll have you do a couple. This one looks like it's right at 52, right there. So I'm going to say it's 52.0 milliliters, and I'm done. This one, it goes in increments of 1, 35, 36, 37, 38, 39, 40. It looks to me right at 37, so I'm going to write 37.0 milliliters. One more. It goes in increments of 2.5, 20, 22.5, and 25. It looks like it's a little bit above 22.5, so I'm going to say it's 23.0 milliliters. What I'm certain of, plus one more digit. Please go ahead and try these 3 on your own. The first thing you need to do is determine what its units are. Sorry, we know that it's in milliliters in this particular case. I'll tell you that. And so you need to measure this liquid that's in each of these graduated cylinders. And their graduations are a little bit different for each one, so you make sure you're being correct. Please try the one on the left. Try the one in the center. And do the one on the right, please. All right, excellent job, you guys. How about if we don't have liquids, we have volumes. We need to measure the volume of a solid. So, for example, we can measure the volume of solids by using certain mathematical relationships. We realize to get the volume of a cube, for example, you can measure the length times the width times the height. And so I could do that. It'd be 10 centimeters times 8 centimeters times 9 centimeters. If I multiply that out, 10 times 8 is 80. 80 times 9 is 720 centimeters cubed. It just so happens that centimeters cubed and milliliters are exactly the same. So 1 centimeter cubed is equal to 1 milliliter. So we can use those interchangeably. So I could say 720 milliliters if I wanted to, but since we measured the length times the width times the height, we measure in cubic centimeters. Sometimes we measure the volume of a cylinder and we use a different mathematical relationship to that. However, let's say we have an object like this rock that we see here, and I want to measure the volume, the space that it takes up. We can use an indirect method to do this. In this indirect method, we use what's called the water displacement method. So first I take a graduated cylinder, it's this one on the left, and I'm going to get the volume. It looks to me it's right at 200 milliliters, so I'm going to go ahead and write that. 200.0 milliliters. What I'm certain of plus one more. And then I drop the rock into the graduated cylinder, and I see that it rose from 200 to 220, 240, 260, 280, 300. It looks to me it's right at 260. So I'm going to set 260.0 milliliters. So how much space did that rock take up? Well, since the volume increased from 200 to 260, the difference is 60 milliliters. That is the volume of that rock. This is called the indirect method for measuring volumes, because not every piece of solid object that we're going to measure is going to be exactly length times width times height, or our perfect cylinder. It's going to have an irregular shape, and so we have to use an indirect method to do that. Please go ahead and determine the volume of this object by using the two graduated cylinders. Awesome, thank you for doing that. A couple more that we need to go over. Mass. Mass is easy. Remember, it's the amount of matter in an object. The amount of matter in an object. And the unit we use in chemistry is the gram, and in science is the gram. The piece of equipment we use, which we've already used a few times, is an electronic balance, and we're getting some newer ones in here soon, so it'll be even more precise. And so we just measure what exactly, we write down exactly what is measured on the balance. We don't have to do anything extra here. We have to measure what we're certain of plus one more digit. It tells us exactly that mass, and that's what you're going to write down when you're using your electronic balance. Most of the time, we're either going to use kilograms, grams, or milligrams, like when you're purchasing, for example, medication is measured in milligrams. So we're going to be looking at the difference between those in just a second. It's really just powers of 10. The other thing that we want to make sure that we know how to measure is temperature. And you've measured temperatures a few times already in the lab, but we're going to be more precise from this point on. And so temperature is just a measure of the average kinetic energy of the particles. And we usually use these alcohol-based thermometers, which has a bulb down here. And as you have things hit it more, it increases the kinetic energy. The more energy that those particles hit it with, that's going to cause the bulb to expand, and it expands upward, and we're able to measure the temperature of that particular substance. If it cools, it contracts and goes the opposite way and cools down. Those are beautiful arrows. Thank you so much for that. So when we measure temperature, we're just measuring the kinetic energy of those particles. So let's measure a couple. Notice, we usually use Kelvin, which we have not learned yet, and I'm going to teach you that here in another couple days. And we use Celsius quite often. The piece of equipment we use obviously is a thermometer. So here's a couple examples. Let me go ahead and do this first one. The first one I see, it looks like to me it's right at -20 here, -10. So I need to be as precise as possible. They go in increments of 1. It looks like it's 19, -19, -18, I think it's right at -17 degrees Celsius. But I don't just write -17. I write -17.0. What I'm certain of, plus one more digit. All right. Over here, it looks like to me it's exactly at 31. So I'm going to write 31.0. What I'm certain of, plus one more digit, degrees Celsius. And last but not least, this one looks like it's exactly at 41. So I'm going to write 41.0 degrees Celsius. What I'm certain of, plus one more digit. Let's have you try 4, 5, and 6 here. So I'll zoom in on number 5 for a second here. Get that measurement, please. Here's number 6. If you'd get that measurement, please. And number 7. If you would get that measurement, please. Excellent. So we have the simple idea of the basic units for length, mass, volume, and temperature. We also need to make sure we know how to convert units. For example, if I was talking about the distance from here to Hawaii, the distance is about, in meters, it's about 4 million meters. That sounds weird. Hey, I'm going to travel 4 million meters to Hawaii right now. So we use what's called a prefix called a kilometer. And that means that it's about 4,000 kilometers, which is around 2,485 miles, but it's about 4,000 kilometers away. So we need to use prefixes. So I'm going to teach you how to convert or change units very quickly. And there's two key steps we're going to follow. Before we do that though, you'll notice in your notes, I have a whole grid for you of the key basic units and the key prefixes we're going to use. I'm going to quickly go over these. I'm going to write these in here right now. Once I've written them, I think you should pause the video and then just type those into, using your Kami, type those in to your notes, please. So let's go ahead and take a look here at a few key things. One, we start off here with the basic unit. So the basic unit is here in the middle. This is the basic unit. And we've gone over these basic units in this video. We have the unit for length, which is the meter, the unit for mass, which is the gram, and the unit for volume is the liter. If we want to talk about smaller amounts, we go to the right. If we want to talk about larger amounts, we go to the left. And so we notice already the prefixes for the meter already here. We have a megameter, which is 1,000,000 times the size of a meter. So if I took 1,000,000 meter sticks and put them together, that'd be a megameter. Or a kilometer is 1,000 of them. A hecto is 100, deca is 10. A deci is 1/10 or 0.1. A centi is 0.01 or 1/100th. A milli is 1/1000th. A micrometer is 1/1,000,000th. And then a nanometer, 1/1,000,000,000th of a meter. So very, very small amounts. Why do we deal with such small amounts? Remember, atoms are super, super small. And so we quite often will use nano and micrometers when we talk about the very small parts of atoms. Okay, so let's go ahead and fill it in for gram. We use exactly the same prefixes. We have a megagram, a kilogram, a hectogram, a decigram is DAG. Sorry, a decagram is DAG. A decigram is DG. A centigram, a milligram, a microgram, and a nanogram. This little symbol you guys will see here is the Greek symbol mu. And that Greek symbol mu, mu is how you pronounce it. Mu is the micro, stands for micro, so it's a microgram. We also have the prefixes for liter, which would be a megaliter, a kiloliter, a hectoliter, decaliter is DAL, deciliter, centiliter, milliliter, which is the one we use most often, a microliter, and a nanoliter, which is very rarely used. So we need to be able to convert from one unit to the next, and so I'm going to teach you a simple rule to do that. There's two key steps we're going to follow. First, count the number of steps from the first unit to the second unit. Move the decimal the same number of spaces in the same direction. So on our worksheet, we're going to do the following. I'm going to change 4 kilometers to centimeters. Okay, so I'm going to have 4 kilometers. I'm going to go to kilometers. Here I am, and I need to go to centimeters right over here. How many places do I have to move? 1, 2, 3, 4, 5. I need to move my decimal 5 places to the right. Well, where's the decimal for the number 4 kilometers? Well, it's right behind it. So if I move it 5 places, 1, 2, 3, 4, 5, I put zeros in there. And we see that we have 400,000 centimeters, the answer that we got here. Let's go ahead and do 4 practice problems together. Once we've done these 4 practice problems, I'm going to have you do a few on your own to make sure you know how to convert units accurately. So let's go ahead and do that. The first one we have is 48 centimeters, and I want to change that to millimeters. So I'm at centimeters, and I want to go to millimeters. The rule states I move the decimal the same number of spaces and in the same direction. So I count the number of places, I moved it 1, so that number would be 480 millimeters, which is the same as centimeters. The other way you can think about it is that these are multiples of 10. So when you're going to the right, you're multiplying by 10, and you can divide going the other direction, and you divide by 10s. So 10, 100,000, there's 10, here's 100, here's 1,000. So each unit we go across is 10 times that amount. So the next one, 6,134 grams to kilograms. So I'm going from grams, and I'm going to go to 1, 2, 3 places to the left. Either I divide by 10, 100, 1,000, either I divide by 1,000, or the easier part is I move my decimal 3 places left. Here's my decimal, so let me write it larger up here, 6134. Here's my decimal, 3 places left, 1, 2, 3. That'd be 6.134 kilograms. Or if I took 6,134 and divided by 1,000, we'd get 6.134 kilograms. All right, moving on. 871 hectoliters to centiliters. So I need to find hectoliters. Here's hectoliters. And I need to go to centiliters. 1, 2, 3, 4 places to the right. So I'm going to move my decimal 4 places to the right. So if I have this number, 871 My decimal is always at the end if it's not shown there. So 4 places, 1, 2, 3, 4 places to the right, 1, 2, 3, 4. I can plug in my number there, and that gets me 8,710,000 centiliters. I did not write that very nice. Let's write it again. 8,710,000 centiliters. All right, next one, 0.007 meters to millimeters. All right, so I'm at meters, and I want to go 1, 2, 3 places to the right. So if I move my decimal 3 places to the right, that's easy enough. 1, 2, 3, that's 7 millimeters. So we can convert from one unit to the next by using this simple little chart, this metric unit prefix diagram that I've given you that you've copied down. Please go ahead and do these 6 problems now. Okay, thank you guys for doing that. You have now learned the key parts of the metric system that we need to know. We've learned about length, mass, and volume. And in particular, we're going to be able to use all these units throughout the year, and we can use our prefixes to talk about larger or smaller amounts. Great job, everybody. Have a wonderful day.